Alrighty, welcome everybody to the 4:30 live stream of our tour of the universe. We're located here in San Francisco at the California Academy of Sciences and the Morrison Planetarium, of course. And I just want to, for the first time, introduce myself. You probably heard my voice a few times. My name is Christian. I want to be your planetarium presenter. And if you haven't been to the stream before, I invite you because it's by far one of my favorite things to do here. We're doing a show right now that's about 30 minutes long. It's completely live. You're going to hear my voice. I'm going to be free flying us. And this show that we're going to be doing is called Tour of the Universe. And it's an immaculate show because we're using a really cool software here called OpenSpace. So we're going to be using this awesome software to fly us through the universe. And what the show entails, well, we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out to the very edge of the universe, the observable universe. So hopefully by the end of the show, you won't have an existential crisis of where we are in space. But I do need to warn everybody, we are pretty small in the grand scheme of things. So I just want to introduce myself. My name's Christian, and it's good to see everyone here. But otherwise, I'm going to be putting us back onto our software so we can get a look at that. There we go. And to start off our show, folks, we're going to be starting pretty close to our planet Earth. We can start to see the city lights of our city of our Earth down below, but we're starting off at the spacecraft right in front of us called the International Space Station. A lot of people like to refer to it as the ISS for shorthand. And a lot of people tend to ask me, "Hey Christian, what is the International Space Station? I always hear it about in news and articles, but I don't really know what it is. Could you explain it for me, please?" Well, of course, folks. The International Space Station is a research facility, a laboratory that orbits around our planet Earth. And they conduct all different types of science experiments that it's a little bit harder to do closer to Earth because there's a lot more gravitational influence. So up here, there's much less gravity. And some of the different experiments they'll conduct up here are things like what happens when you try to grow plants in space? Do the plants grow the same? Do they grow differently with less gravity? Which way do the roots grow? And another one is what happens when you try to spark an open match in space? Does that act the same? Does that act differently with less gravity? And one of my favorites by far is where they had two identical twins. One twin lived on Earth for about a year, the other one lived on the International Space Station for a year. After that year, they compare and contrast the two twins. Turns out when you live in space for a long period of time, you tend to age a little bit slower. But not only that, you also lose a lot of muscle because you don't have gravity constantly working down on your muscles all the time. So if you plan to live in space for a long period of time, remember to exercise. And also, folks, this space station looks really big here in our software, but it's not that big in actuality. It's only about the size of an American football field. So if you've never been to an American football game, and if you visit the California Academy of Sciences, that's about how big, that's about the size of our museum. And also, what's really impressive is that this spacecraft is going incredibly fast. The International Space Station's traveling at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And this also looks really far away from our Earth, but it's not that far either. The International Space Station is only about 225 miles above the surface of our world. 225 miles. In terms of California, that's not too far away in distance. That's like going from San Francisco to Santa Barbara. That's like a nice little road trip to get away with the family for the weekend. So, not too bad. But to tell you the truth, folks, this is as far as we put humans into space nowadays, only 225 miles above the surface of our world, because traveling into space is whew, very, very expensive. You got to build yourself a rocket ship or buy yourself one, and then you have to account for a whole lot of rocket fuel. You're going to need so much rocket fuel to get away from our Earth. And then you have to also account for all the food, water, and all the air you're going to be breathing while you're up here in space. So the bill gets quite costly quite rapidly. But for now, the International Space Station is just the first stop in our tour of the universe, so we're going to see it slowly disappear to the city lights down below. In fact, before we lose track of it, I want to add a nice little orbital path so we can see it, so we don't lose it to all the lights. But now we're going to see it slowly fade away. And all those city lights that we were seeing at the beginning of the show, that was Egypt and the Nile River, so glows the illumination is quite high at night. But now we zoom so far away from the Earth, we're now able to see our entire planet Earth. And I want to let you know again, the software that we're using here for the show is called OpenSpace Project. So if you want to fly through space just like how I'm doing right now, you're more than welcome to do it. This is an open source software, so anybody can download this. But just a warning, this uses a whole lot of processing power and information. So if you have an older computer, you may want to rethink it. But if you got something new like a gaming computer, give it a try. It's a whole lot of fun. Just go to your favorite search engine, type in Open Space Project. You'll come across the link and download it. Otherwise, if you just put in open space, you might get a furniture store. So just a heads up. And also, if you're a person like me that doesn't want to download anything, you just want to fly through space, we also have another great alternative called NASA's Eyes. So just like the human eyeball, go to your favorite search engine, type in NASA's Eyes, and they have different profiles, and you can fly through space without having to download anything, and it's so much fun. But right now, we're using OpenSpace, and it's such a wonderful software. But now that we got a sense of what we're using here, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we've been to the moon before, but that was a little while ago. That was between 1969 and 1972, thanks to NASA's six Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science, and of course, they had some fun. They got to play some golf up here as well. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon thanks to NASA's new space mission called Artemis. With this new series of space missions, NASA wants to send humans eventually to Mars. But before we send humans deep into our solar system, we got to figure out how exactly we're going to be living out here in space. So the moon is the perfect stepping stone to figuring out the logistics of how we're going to be doing that. And what's really amazing is that they're going to be sending the first woman to the moon. But not only that, they're also going to be sending the first person of color to the moon. But not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to do a lot more science in a much more compactable size. And one place where they want to set up a lunar base is going to be the south pole of the moon. The reason why is because we found ice there, and ice is going to be very helpful because you can melt that, you can pass electricity through the water, and then you can get hydrogen and oxygen, and both of those are very valuable when you're way out here in space. So again, we humans should be heading back to the moon in the next few years thanks to the new Artemis space mission. So look out for any news about them. And folks, sometimes when we're looking at the moon here from Earth, especially when it's really close to the horizon, it feels like you can reach out your arms and touch the moon. It feels incredibly close. But the moon is incredibly far away. It's about 240,000 miles away from the Earth. Whew, 240,000 miles. Some of our viewers today may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it. The roads out here towards the moon, they're poorly maintained. Hee hee hee. And from here on now, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. Instead, astronomers use a more convenient measurement known as light speed. Now, light travels at a mind boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So, while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everybody say bye bye, moon. And now we're going to start to see the moon start to slowly disappear in the vastness of space. In fact, before we lose track of it, just like the International Space Station, I want to add some nice planet trails so we can see where everything is, because again, space is so vast. And now we're going to see the moon and the Earth's orbit as they start to slowly recede. And on our journey, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to computer models like OpenSpace showing us the most accurate images and information available to us. And now, folks, the nearest star to us, the sun, should be coming into view. So here comes the sun. Do 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 do. And folks, the sun is also really far away from our planet Earth. It's about 93 million miles. Whew, 93 million miles. That is a good distance away. And again, we're the third rock from the sun. So we got Mercury here, Venus there, and Earth, third rock from the sun. 93 million miles between us. In order for sunlight to travel that distance, it only takes sunlight about 8.5 minutes at the speed of light to cross that distance. 93 million miles. Whew, that's incredibly fast. And again, this is such a cool concept to keep in mind because let's say the sun was to turn off all of a sudden, and there was no more sunlight being emitted, that last bit of sunlight will travel that 93 million miles, that 8.5 minutes, and then all of a sudden, the daytime on Earth would become nighttime. And again, such a cool concept to keep in mind because let's say we're looking at a star that's, let's say, 70 light years away from us. Well, we're looking at that star as it looked like 70 years ago because the light that just reached us took 70 years to travel that distance. So when you look at really far away objects in space, it's kind of like looking back in time in a sense, which is pretty cool. But now we have a nice bird's eye perspective of our solar system. So let's get a quick crash course of what we have. So right in the middle, we have our star, the sun, the biggest thing by far. The closest planet to the sun, again, we have Mercury, we have Venus, Earth, that's us, and then Mars right over here. These are the rocky terrestrial planets. These are places where we can actually land a spacecraft and walk around on. And then past the orbit of Mars, we have this really cool thing called the main asteroid belt. And this is what it would look like if I highlight all the asteroids in our asteroid belt. There is a whole lot of them, folks. And then past the asteroid belt, we have the really big planets, the gas giants, the Jovians. We've got Jupiter, the largest of them all, right over here. Then we have Saturn, famous for its rings. And then past them, we have our icy gas giants. We got Uranus, the funny one, and Neptune right over here. And of course, we can always add everyone's favorite and lovable dwarf planet, Pluto. So here's the orbit of Pluto on screen, just on the very top, bottom left. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And I know a few of you out there are probably wondering to yourself, what's the Kuiper Belt? I've never heard of that before. Well, folks, the Kuiper Belt's going to be all this stuff. Whew, that's a lot of stuff, right? So, folks, the Kuiper Belt is kind of like a second asteroid belt, just way out here past the orbit of Neptune. And what you're mostly going to find out here are icy asteroids and short period comets, comets that don't stray too far away from the sun. They have a nice little short trajectory, like so. And what was really fascinating is that in 2006, our space telescopes and technology greatly improved. So we were able to find a whole bunch of these objects in 2006. We found more than 400 objects out here. And some of this stuff was bigger than Pluto. So we couldn't call all these things planets. There's just way too many of them. So all the astronomers and scientists on planet Earth in 2006 had a great big meeting. They had to figure out what exactly you need to be considered a planet. And they came up with three different criterias. And unfortunately, that was the day when Pluto went from being a planet to a dwarf planet. So, because we found all this stuff out here in the Kuiper Belt region. And that's the really cool thing about science because as our technology improves and gets better, we're able to find much more objects way out here and we can redefine what certain categories like planets are. So, really cool stuff. But I'm going to put away the Kuiper Belt because that's just a whole lot to look at. And now, folks, I'm going to be adding on screen some of the many different spacecrafts we sent out in the 1970s to explore our solar system. So now on screen, we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. You can actually see that interaction as we fly by. There's that New Horizons trajectory. So 2015 was a little while ago. Now, just to let you know, all these spacecrafts are traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventurers, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours. That's not too bad. But it's time for us to leave our planetary scale behind and now step into interstellar space, the space between the stars. Distance now becomes so immense, folks, that it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And now we zoom so far away, folks, that now our star, its glow, becomes just one of many other stars here in our star field. And I just want to make sure we got the right star system. Yep, right here. So this is our solar system right in the middle of our screen. And then just down here, that's Alpha Centauri. Again, 4 years at the speed of light to get this far. But that doesn't really put into perspective of how long it would take us humans to travel that distance. Well, folks, if you're getting a rocket ship of today's capabilities, left our Earth, made your way over to Alpha Centauri, it's going to take you about 8,500 years to make that trip. Whew, and that's just a one-way trip. I don't think I could live that long. But, folks, let's stop and consider whether humanity has made its presence zone beyond our solar system, because now we're stepping inside something called the radiosphere. So, again, here we are inside the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And this extends about 90 light years in all directions, emitting out from the Earth. Now, this first began in the early 1930s with strong radio waves, early television, radar signal, and then later the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that, but the earliest radio was not quite powerful enough to escape the Earth. And since all these signals are electromagnetic, they are traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is always expanding at the rate of 1 light year per year. So is anybody out there listening? And now, folks, I'm going to be adding some many markers onto the screen. These markers indicate some of the many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth like with conditions suitable for life as we know it. So far today, we found more than 5,000 exoplanets in the nearby vicinity to us, 5,000 other worlds besides our own. And that 5,000 number is going to be increasing as the years continue because we have spacecrafts or space telescopes where their whole purpose is to find as many exoplanets as possible. So as they continue to scan more and more of the night sky, they're going to be finding exoplanets left and right. In fact, we pointed our space telescopes in this direction, and again, we found a whole heap. So again, as they scan more, they'll be finding exoplanets as they continue that search. Not to say if any of them are Earth like with conditions suitable for life as we know it. Well, we can't answer that question quite yet. New generations of space telescopes are being developed right now, so those are on the drawing boards. They have to be constructed, launched into space. So we've got a little while before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we live over here in this star system. We find an alien civilization on the other side, let's say over here on our right side of the screen. We say, hey, we're humans. We send a message, takes 60 years to get to them. They listen in, answer back, another 60 years to get that return message. Folks, that is a 120-year conversation in the making. And again, I don't think I can live that long. And of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And for now, I'm going to be putting away our exoplanet markers away, and I want to leave our radiosphere up on screen because, as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. Alrighty, folks, we zoomed all the way out, and now we're able to see our entire Milky Way galaxy. And I've got to ask, can anybody here see their house from here? Probably not. We're way too far away. And folks, our Milky Way galaxy is incredibly large. In order for you to cross it from one side to the other, it takes about 130,000 light years. It's about 130,000 light years across, so a good distance. And our Milky Way galaxy is so huge, we estimate that there's at least 300 billion stars in our galaxy. If our recent discovery of so many exoplanets just within our small neighborhood within this vast star city is any indication, there could be billions of planets and potentially millions of Earth like planets throughout our single galaxy. And before we leave our Milky Way galaxy, I want to show you what it looks like from a sideways point of view. As we start to swing around, you're going to notice that we live in a big flat spiral disk. Kind of looks like a big pancake in space. And this is important for two reasons. One, you've probably gone camping and you were out at night and you probably heard someone say, "Hey, look, you can see the Milky Way from here." What they're referring to is the Milky Way plane. That's what you're seeing up in the night sky, that band of stars. And two, this is important because when astronomers and scientists want to learn about the universe, it's so much more easier for them to point their telescopes galactically north and galactically south instead of looking through the plane of the Milky Way, because there's so many stars, planets, uh, debris, gas clouds, things that block their view of the universe. So again, we like to point our telescopes galactically north and south. That's going to come important in just a little bit. But, folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So, in this giant leap, every single point of light they are seeing no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. Now, we live in a local galaxy group, which contains about 30 galaxies large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as we continue zooming out, folks, you're now going to realize that galaxies are not evenly distributed throughout space. They're not uniform. Instead, galaxies like to group together in large groups and clusters, or they like to avoid each other where there's very few galaxies or no galaxies at all. Voids. And we can see a nice galaxy cluster over here on our right side of the screen. We can see some voids or very few galaxies on the left hand side of our screen. You can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And folks, we zoom so far out now that the this picture represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing astronomer by the name of Dr. Brent Tully, who worked at the University of Hawaii and compiled this amazing representation thanks to the work of dozens of other astronomers aside him over decades of time. So big shout out to Dr. Brent Tully. I love flying through this galactic map. But now we have automated systems that are mapping even the most distant galaxies. So, folks, we're now about to see the large scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. Whew. And just to let you know, our large scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I mentioned that we live in a big flat spiral disk of our Milky Way galaxy? Well, if you were to line up the plane of our Milky Way, it would line up and down just like so. And again, we like to point our telescopes galactically north and galactically south. But we still want to make sure that there was galaxies. So eventually, we normally have a data set right here that will show galaxies, but there's just not as many and not as farly found. They usually go about here or so. But pretty much we have to wait for our technology to improve. Once that happens, we'll be able to map out all these areas that haven't been filled in yet. So we just got to wait for that technology to be invented. So we got a little while to go, but eventually those will be filled in. But now, folks, we got to continue pressing on because we're running short on time. And now we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of our screen. So those orange dots, those are the quasars. And quasars are short for quasi-stellar radio sources. And these are blazing objects that are billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenager version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge of the observable universe. And what we're looking at is called the cosmic microwave background image, or the CMB image for short. Now, all evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this picture is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, this is a temperature density image where the light echoes of the Big Bang are color coded, with the lighter areas corresponding to the hottest, least dense regions, and the darker areas, the coolest, densest regions. These fluctuations in temperature and density are extremely, extremely tiny. They vary no more than 1 part per 100,000. But these really tiny differences eventually gave rise to that large scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, folks, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But, folks, we've traveled as far back as the law of physics can physically allow us to go, so we only have one direction left to go. That's going to be back towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make our return trip back to our pale little blue dot. Alrighty, folks, we are crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. And we live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of the night sky. All you need is a good pair of binoculars to make for a first decent telescope. And there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But, folks, we just made our way through our Milky Way galaxy. We headed straight through that radiosphere. We're making our way to our star system, our solar system, our neighborhood in space. And now we're about to pass the spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt, making our way to the third rock from the sun, our home world, planet Earth. All the people that we know, love, ever learned about in history all lived on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, folks, this is going to be the end of our tour of the universe show. And I want to thank y'all for stopping by and watching it with us this afternoon. I hope you really did enjoy it. But otherwise, we made it back home safe and sound just in time for lunch or for dinner. And I want to thank y'all for stopping by and watching it with us today. I hope you had a great time. But otherwise, that's it for now, folks. And I hope you have a great evening. Take care.